Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Izzuddin Ismail bin Ismail, a final year student of School of Mechanical Engineering, UiTM Shah Alam. I will present my final year project which entitled The Study of Airflow in Model Room with Upstream Object. For information, my FYP project was supervised by Puan Nur Melissa binti Ali. The panel for my FYP presentation are Dr. Muhammad Fairuz bin Ramli and Dr. Wan Ahmad Najmi bin Wan Muhammad. I will start the presentation with project summary. The objective of this project is to investigate and study the airflow in model room with the presence of nearby buildings with different size and distance. The method to achieve the objective of this project is to use any engineering simulation commercial tools. The fluid analysis of model room will be tested with different size and distance of upstream object to provide the optimal airflow for the room's thermal comfort. Next, we will go to introduction. Natural ventilation is a method in which the interior air of an enclosed area is continually replenished by fresh outside air through openings for improved thermal comfort and indoor air quality, without the need of forced flow. For the weather in Malaysia, which is known to be quite hot, natural ventilation can reduce the reliance on air conditioning systems, resulting in lower energy usage and greenhouse gas emissions. For the study, the observations are based on air velocity to define the best thermal comfort in a building. We continue the presentation with problem statement. The effect of nearby buildings has lately been recognized as a critical influence on the ventilation rate when estimating the airflow of a building or room. The influence of the size and distance of neighboring buildings on the ventilated flow will be examined in order to reduce costs and offer maximal thermal comfort in the building. Next, we will go to objectives. The main objective is to study the effect of upstream object with different distance and size to ventilation rate in model room. The second objective is to study and examine the airflow inside the model room, and last one is to achieve optimal thermal comfort in building. For the scope of work and limitation, there are 4 cases of upstream object with different size and distance to be tested and investigated using CFD analysis, and the wind flow will be subjected to 3 meter per second speed for every conditions. Next, we will go to methodology. The project starts with creating a model room in CATIA with various sizes and distance of upstream object, then import the geometry model of CATIA into ANSYS. After that, grid independence tests in ANSYS will be run and set up the simulation cases by using ANSYS features to achieve the objective. The data outcomes of the simulation that has been completed will be analyzed, and lastly, result validation. Next, we will go to geometry model. The geometry model will be searched in previous article and journal to get a suitable dimension for model room. The model room will be created with dimension of 0.8 meter length, 0.4 meter width, and 0.4 meter height with 2 inlet and outlet opening windows. The windows dimensions are 0.12 meter at the center plane of the wall and will not exceed 10% of the wall's area. The upstream object will be created in 2 designs, which the length and width are the same for both designs but different in height, which are 0.4 meter and 0.8 meter respectively. We continue the presentation with list of cases. There are 4 cases that need to be analyzed. For the first case of this study, the upstream object will be created the same size as the model room. The upstream object will be in rectangular size with 0.8 meter in length, 0.4 meter in height, and 0.4 meter in width. The distance between model room and upstream object will be 0.4 meter. For the second case, the upstream object's height will be increased twice the height of model room, which is 0.8 meter in height. The distance between upstream object and model room will remain the same as first case, which is 0.4 meter. The third case of the study shows that the upstream object will have the same size as model room. But the third case, the distance will be twice the first case, which at 0.8 meter between upstream object and model room. For the last case of the study, the upstream object will be the same size as second case, but the distance between upstream object and model room will be 0.8 meter in length. Next, we will move to numerical setup for CFD analysis. The first one is turbulence model. For turbulence model, K epsilon will be implemented and selected. The model was selected because it is a commonly used model to stimulate airflow. The boundary condition was set based on the previous study because it is the best practice that can be used for modeling of wind flow in an urban area. The setting of boundary condition are set as shown in the table. Before starting the real CFD simulation, the grid independence test must be completed to determine which number of elements will produce the most accurate for experimental results. From the grid independence test result in the table, the find case shows the closest number of elements and nodes to the reference data. The find case will also be chosen to create meshing because of less error compared to the others. The coarse and medium case take a bit shorter time to mesh than the find case, but the find case mesh much better than the others since the number of elements is significantly greater. Next, we will go to ANSYS result. The contour and streamline results from ANSYS Fluent reveal that the velocity in the model room differs significantly from the outside velocity, where the red, yellow, and green contour and streamline can be observed. To analyze the amount of velocity within the model room, a line will be constructed inside the model room from multiple axes, which are X, Y, and Z axes, based on the contour and streamline results. The velocity of each case will then be produced in a single graph with X, Y, and Z directions. Next, we will continue on velocity charts. The first velocity chart is in x-axis direction. The graph pattern shows a slightly different for each cases, where it can be seen that the airflow rate increasing from the start and then continuing to decrease at the middle of building. The airflow of each cases then continuing to increase at the end of model room. The graph patterns are the same because the airflow is higher at the opening windows at the start and end of the room. The starting airflow will be more than the end because the wind came from the inlet of domain. It can be observed that case 1 and case 3 has the highest opening air velocity at 1.105 meter per second and 1.147 meter per second respectively. For the velocity chart in the y-axis direction, the graph patterns reveal similar findings for each case as the air velocity begins at 0 and increases toward the center of the building. The air velocity then fluctuates slightly for each case before dropping significantly in the middle and reaching 0 at the end of the graph. Because of the higher and lower walls in the y direction, the graph was at 0 at the beginning and end. The graph rises in the center as a result of the air velocity entered at window opening and gathered in the center of the room. It can also be seen that case 3 has the maximum amount of air velocity when compared to others, which is 0.251 meter per second. Lastly, the graph pattern for velocity chart at z direction displays similarities for each case where it began with 0 and ends with 0. The air velocity then begins to rise from 0 and fluctuates at the model room's center. The air velocity then started to drop until it reached 0 at the other end of the model room's wall. The graph represents an increasing volume of airflow in the center as a result of air entering via the opening window and exiting through the opposite window. Finally, case 3 has the highest air velocity compared to the other cases at 0.148 meter per second. To conclude, according to the velocity charts graph, case 3 with an upstream object the same size as the model room but twice in distance offer the maximum thermal comfort in the model room since it achieved the largest amount of air velocity compared to the others. For recommendation, the future researchers should consider the impact of upstream object to the airflow in wind catcher. It also has to recommend to consider on the outside temperature of building. And last but not least, consider the number of occupants in the building while performing the simulations. That's all from me. For further question, these are the contact detail that consists my number, phone and email address. Thank you for listening.